Hey guys, in this video we're just going to have a quick look at a molar heat capacity example. It's quite a big one, but what's nice about it is that it will pretty much join together everything we've learned so far in the thermal physics topic. Right, so let's have a look at what it says. A temperature of 7 moles of an ideal diatomic gas is increased from 200 degrees Kelvin to 264 degrees Kelvin. If this process is isobaric, find the work done by the gas. Right. So, I need to find the work. First thing I'm thinking is of the first law of thermodynamics. And I'm thinking that if I can find the heat and the change in internal energy, I can actually find this work. And we've discussed formulas for both of these that will allow us to find their values based on the information we've been given. And so that'll help us find the work. Right, so first let's look at the heat. And from that previous video, we discussed molar specific heats. Now which C do we use? Well, the process is isobaric, meaning constant pressure, so we use CP. Right. CP, if you recall, was F plus 2 over 2R. And in this case, we've got a diatomic gas, and it's above 100 degrees Kelvin but below 1000, and so it actually has 5 degrees of freedom. So that gives us Cp equals 7 over 2R. And so our new formula for our Q is equal to N times 7 over 2R times triangle T. Right. So now we can start subbing in some values. Our N is 7. R was 8.314. And our change in temperature, 264 minus 200. Right, put that all in the calculator. And we end up with the heat added being 13036.352. Just going to put those on so that we don't round off anything important. And that's in joules. Right, so new page. Now what we're going to do is look at the another formula that we've seen a few times now off our formula sheet, which is this one. Right, so the normal one we use actually has NKB over there. They're both on your formula sheet, and basically NR is equal to NKB, and I'll leave that as an exercise for you if you want to prove that. But otherwise we're going to use this formula because we're given moles rather than number of molecules. So the degrees of freedom, if you recall, was 5. The number of moles was 7. Gas constant 8.314. times the change in temperature. Right, put that all in the calculator, and we find that the change in internal energy is 9,311.68 joules. Right, so from our first law of thermodynamics equation, we get this one. Right. So it's just a simple rearrangement, and then we can now sub in our values that we just worked out, which was our change in E int 9311.68 and our heat added from the other page. Right, now we can just put that in our calculator, and we find that the work done minus 3724.67 joules. Cool, so from very little information we found this value, and the way we interpret it is that the work was done by the gas on its surroundings because it resulted in the loss of this amount of energy. And that concludes the molar heat capacity example and this video. Thanks guys.